Hey everybody, it's Mr. Carr again. Today we're going to be talking about 3-4 day 2. So we get to solve more exponential logarithmic equations as well as model with our exponential equations. Okay, so when we look at this example here, we want to solve e to the 2x plus 1 equals 8. So one of the easiest ways to do this is basically applying our one-to-one property. If we evaluate the natural log to the left side and to the right side. So if this is true, then that means, let me rewrite this, this is true. Okay, so it's just working backwards from that one-to-one property. Well, if I take the natural log of this, I chose that because natural log of e is basically going to cancel that out. So this will be 2x plus 1 is equal to the natural log of 8. So now I'm just solving for x. And natural log of 8 is going to turn into basically any other decimal number. But for now, I'm going to leave it like this. So 2x equals the natural log of 8 minus 1. Take everything divided by 2. So x equals the natural log of 8 minus 1 over 2. Now it does say round to the nearest hundredth, so I'm going to plug that in my calculator. So I'm going to do the natural log of 8 minus 1, and then divided by 2 is going to give me about 0.54 for the nearest hundredth. Okay, so that is one of our main goals here is we're going to undo like these base e's with our logarithms. So I use natural log here because that's going to cancel out the base e. Here it gets a little bit tricky. We have base 3 and base 2. Normally we would put things in the same base, like if I have base 2 on both sides, that makes it easier. I can't do that in this case. There's a couple things I could do. One way I could do it is just evaluate log to both sides. So I take the log of 3 to the 6x minus 3 equals log of 2 to the 4 minus 4x. Again, the one-to-one principle says that if this is true, then taking the log of both sides is also going to be true. All right. So from here, I've got exponents. So I'm going to take the entire exponent, bring it to the front. So I'm going to have 6x minus 3 times the log of 3 equals 4 minus 4x times the log of 2. In order to solve for x here, I'm going to want to bring x's together somehow. So I'm going to bring them to the same side. So before I do that, I'm actually going to need to distribute the log of 3 and the log of 2 in this equation. So I'll have log 3 times log 3 times 6x minus, it might be, yeah, I think I'm going to put that in the front. I'll say 6x times log of 3, and then minus 3 times the log of 3, and that's going to equal to 4 times the log of 2 minus 4x times the log of 2. So I want to bring all my x's together. I'm also going to bring this to the other side. Okay, so I'm going to add 3 log of 3 over. And I'm going to add 4x log of 2. Now I cannot combine this because they are log of 3 and log of 2. So I'm simply going to just add it over here. So I'm going to add 4x log of 2. So we got 4x log of 2 plus 6x log of 3 is equal to 4 log of 2 plus 3 log 3. All right. Almost there. So now that I have x together, the goal is to solve for this. Since I have two x's, these are common terms, or sorry, common factors. 4 times x times log of 2, 6 times x times log of 3. X is being multiplied in both of those. So I can actually divide, or not divide, I can factor out an x. So x times 4 log 2 plus 6 log 3 equals 4 log 2 plus 3 log 3. And now that I have that in factored form, I could divide out 4 log 2 plus 6 log 3. And that's going to divide out to both sides. Okay, so this, it does say round to the nearest hundredth. Before I do that, this is what's going to go in my calculator. 4 log 2 plus 3 log 3 divided by 4 log 2 plus 6 log 3. This is what's going to go in the calculator as a whole. In a way, this is like my exact answer. Okay, this is as simplified as I can get with that one. If I plug in all my calculator at once, so I got 4 log of 2 plus 3 log of 3 divided by 4 log of 2 plus 6 log of 3. And that comes out to the nearest hundredth, it'll be 0.65. Okay, you can do this problem with decimals, like probably about right here. Instead of doing it as log 3 and log 2, and I distribute those expressions, you can do decimals, but you need to make sure you use a lot of decimals. So if you evaluate this and this, I would use at least 4 or 5 decimals to distribute out. Then you're just dealing with decimal answers throughout the problem. What I like about this is I'm dealing with my algebra skills. In the end, I have one thing to plug in my calculator, and that's this. Okay. Now, I did this with just log base 10. You can choose any log base you want. It gets a little bit different. Like, let's say if I did, I'm not going to do the whole problem, but at least set it up. If I did log, let's just say log base 3 to both sides. Okay. So if I evaluate log base 3 to both sides, it'll cancel out this side. So 6x minus 3 is equal to log base 3 of 2 to the 4 minus 4x. It's going to be a similar process. I need to be able to get this x out and then factor it out with this x. So I would still take this into the front. I would distribute this log base 3 to everything, then rearrange my terms so I have x on one side and do my factoring. It'll look a little different than this, but it actually will be an equivalent expression. All right. So let's try this one. We're going to solve exponential equations that are in a quadratic form. So what do I mean by that? If you look at this setup, this degree is double that one. I don't want to say degree. This exponent is double that one. Like 2x is 2 times more than x. It's very similar if I want to do this. A squared minus a minus 2 equals 0. So if I follow this quadratic and I do that, I can factor this. It'll be a minus 2, a plus 1 equals 0. A minus 2 equals 0, a plus 1 equals 0. So then a equals 2 and a equals 1. Or sorry, negative 1. Now, if I solve that quadratic, that one feels more straightforward. This is in a similar setup to that. Okay, this is the same thing as if I took e to the x squared minus e to the x minus 2 equals 0. So in a way, what I'm doing here is I'm basically calling a equal to e to the x. So my process would actually start with that. If I recognize that this is double that, then I can call a this e to the x and I just solve out my quadratic. Because now, once I'm at this level, let's bring e to the x back. Okay, so I can say e to the x is 2 and e to the x is negative 1. For here, to solve x, I'm going to put it into like its logarithmic form. So e to the x equals 2 is the same as saying x is equal to the natural log of 2. Okay, so we're taking natural log there. So I plug that in my calculator. Okay, and I get approximately let's go 693. Okay, e to the x of negative 1. This would be the same as taking the natural log of negative 1. However, if I plug that in my calculator, I get an error. Okay, so this one is actually extraneous. So we always want to check for extraneous here with our logarithms because we cannot take a natural log or a regular log of 0 or a negative number. So that doesn't even count as an answer. So I only get one answer here, and that's 0.693. All right, so here's another logarithm. We are going to use our properties of condensing this to put this into a simpler setup and then still do our one-to-one property. So because it's addition, I can combine these into one logarithm, but multiply x times x minus 3. Since I have log base 10 on both sides, then I know that x times x minus 3 which I'm just going to go ahead and distribute that out, is equal to 28. So I went ahead and distribute the x to that. Okay. So now it's just a quadratic. So if I subtract 28 over, it'll be minus 28 equal to 0. We can go to our factoring here. That'll be x minus 7, x plus 4. So I solve them both, I get 7 and negative 4. Well, just like before, there's possibilities that some of these won't work. So I want to check back. Now, if I do the log of 7 plus the log of 7 minus 3, that will check out. That's totally fine. Okay. But if I do the log of negative 4, that's extraneous. Okay. We can't take the log of a negative 4. So that means this one is gone. We only have one correct answer here, which is 7. Okay. So another one here. So we got log of 3x minus 4 equals 1 plus log of 2x plus 3. So one thing I can do is I can, because I have logs on both sides, let's bring them together. I can't actually subtract them, but when I subtract log of 2x plus 3 over like that, so I'm going to subtract this whole thing over is what I'm doing. So after I do that, it's a subtraction problem, so I can condense that down into a division problem. So log of 3x minus 4 over 2x plus 3 equals 1. So in this format, instead of it being one-to-one property, remember this is log base 10. So this is the same as saying 3x minus 4 over 2x plus 3 equals 10 to the first power. Because this is log base 10, I'm going to just take it as 10 to the first power. So from there, I can just do cross multiplication. We're just kind of solving a quick rational equation here. So I got 10 times 2x is 20x plus 30 equals 3x minus 4. And then we'll have, let's see here, subtract that over, subtract 3x over, and subtract 30 over. So we get 17x is equal to a negative 34. And we divide by 17. So I get negative 2. Still want to double check for extraneous solutions. So in this scenario, if I try to plug it in, log of 3 times negative 2 minus 4 equals 1 plus log of 2 times negative 2 plus 3. Run into a problem here, because if I do that, that's going to be log of, that'll be negative 6 minus 4 is a negative 10. 1 plus the log, that'll be negative 4 plus 3 is a negative 1. In both of these cases, I cannot take the logarithm of the negative. So because of that, x equals negative 2 is not an answer, so I have no answers here. It's no solution. So always with logarithms, check for those extraneous solutions. Okay, you want to be on the safe side there. All right, last example we'll go over. So this table shows the number of cell phones a news store sold in March and August of the same year. If the number of phones sold per month is increasing at an exponential rate, identify the continuous rate of growth. Then write the exponential equation to model this situation. So in this scenario, we're going to do a continuous rate of growth. So that is this one where it's n is equal to n sub 0 e to the kt. So what's going to help with this is we have some kind of time frame. So we got to make sure that when we look at our time, we're consistent with our values. Sometimes time can be years, sometimes it can be months. Like in this case, it's going to be months. What we have here is we have n. We have an initial amount of n is 88. What we need to do is to help with this is model the time in some way. There's multiple ways you can do that. So let's say I want to call this time since March. Then I'll call this month 0. So that's March and then August. So we got March and then April, May, June, July, August. So that would make it 0 and 5. So here I'm defining T as my years, or it's not years, months since March. Now, another option is to just go off the months of the year. So where's it at within a year? So if I call January 1, then I could have done this as 3 and 8. So maybe I make that my time. Okay. So it's up to you how you want to do it. Just make sure you keep track of that, because when we go into like the follow-up question down here, where we want to find how many number of months it takes to sell 500 phones, we need to make sure it references back to what it is. Okay. So we're going to go with 0 for now. So if time 0 is referring to March, so we got 177 for n. The initial amount was 88. E to the k times 5. Okay. So our goal here is, so yeah, again, sorry, the 177 is after 5 months. That's why that's there. So I want to solve for k. In order to do that, first thing I'm going to do is I'm going to move this over here, give myself more space, but I'm going to undo this multiplication of 88, so I can just divide that to both sides. So I'll leave that as 177 over 88, which is, yeah, I'll just leave it like that. I'm not going to put the decimal number in yet. I don't like to do the decimal numbers to the very end. So we get 177 over 88 is equal to e to the 5k power. So just like before, we want to get rid of that base e. So I'm going to evaluate the natural log here. So what I'm going to do is I'm going to take the natural log of both sides. That cancels that out. So that's going to turn into the natural log of 177 over 88 is equal to 5k. And from there, the one last step is to find k. I'm going to divide both sides by 5. So I got the natural log of 177 over 88 over 5 equals to k. Now, when I put this into my model, for my exponential growth model, I don't want to do this as like that. I don't want this to go in for k. Like this would have to go in for that. So now I'm going to go ahead and put this in my calculator to get the decimal number. So natural log of 177 divided by 88. Take that divided by 5, and I get 0.13. Let's go 98. I like using more decimal numbers here just so it makes it more accurate in the end. So now we can write our exponential equation. So the number of cell phones is equal to the initial amount, 88, e to the 0.1398 t. And again, this is going to be t as in months since March. So now use your model to predict the number of months it will take for the store to sell 500 phones in 1 month. I can go to graphing for this to help figure out where this is going to be. So if I go to my graphing calculator, so I got 88 raised times e to the 0.1398 t. So go to Desmos, which I do not have from earlier. So I'm going to go make a new one. There. Sorry about that. That's here. It's 88 times e raised to the 0.1398 x. Okay, and I'm going to turn that into a table. So I want to see how many months it takes to get to 500. So we got, let's just jump ahead a bit. I have to jump a lot more. So let's go 10, okay, 11, 12, and 13. There it is. It happens between 12 and 13 months. Okay, so we jumped from 12 to 13. We go from 471 to 541. So that tells me that's months since the initial March year. So basically it happens the following April. Okay, so it happens 12 to 13 months later, or the following March/April. Okay, and that's it. So again, the goal today was to solve using logarithms. That helps us making our new models if we have to find like a continuous rate of growth for our exponential models here. All right, that's it for today. Take care, everyone.